that's out of the way, let's move on. So you've all done the MLF course. So this is perhaps a needless, so how many of you have not done the MLF course? 1, 2, 3, okay. So there are 4 or 5 people who have not done the MLF course. So we will actually do this. So the title of the workshop is Optimization Fundamentals. The reason I had this workshop, other than the reasons that I mentioned, was the level of understanding and knowledge of optimization that is typically present among, let's say, even machine learning research candidates, PhD candidates who come for an interview is not ideal, right? So that's putting it mildly, and because even in the researcher level, I find many fundamental mistakes. That's because of applying the rules somehow mechanically, right? If you apply rules mechanically, you will make mistakes eventually, because you are not always going to get questions in the same format that you have been getting for applying the rules mechanically, and you will have no way to figure out what's going wrong, right? So this is that's the reason why I have this workshop, which is to get you familiar with the absolute basics of optimization. But before we go there, what is optimization, right? The first thing is, we are all doing optimization problems all the time. Even though we might not get the solution, but we are all trying to solve optimization problems all the time, right? So it can be different type of thing. For example, let's say you are in let's say you find 2 roads diverging in a yellow wood, and then you might say, okay, what route to take, right? So you might have well, what do you want to do? Right? So you might say, okay, I want to get to class on time, so might want to minimize travel time, right? Another question might be, let's say you want to decide how much to study or how much to play, but what's the goal, right? So your goal is, let's say, to maximize happiness, but you do want to get into IIT, right? So let's say that means that you want to maximize happiness subject to getting into IIT. So subject to such that constraint, these are called constraints, right? So you have some objective to maximize, but in addition to that, you also have some constraints, right? So in this case, you want to maximize happiness, but you do want to get into IIT, right? So maximize, let's say, current or short-term happiness, but subject to getting into IIT, which kind of captures your long-term happiness, right? So that's the situation. And let's say you want to decide how much to run, or whether to run or bike, and how much. So let's say you want to maximize your calories burned, but you don't really want to exhaust yourself, right? So these are all kinds of optimization problems that you face every day, right? So in your everyday life, you will be facing these problems, whether you are consciously aware of these or not, right? Most of you might be, but once you see this, you will see how you can frame everything as an optimization problem, right? Okay, so that's nice, but optimization happens in nature also, right? It happens through a completely unknown paradigm that you think of. For example, let's say you have a ray of light from A to B, right? So you have this Fermat's principle, which says that light travels in the shortest path possible from point A to point B, right? So A to B, light could have taken this green path, it could have taken this black path, or could have taken this red path, right? Out of all these 3 paths, why did it take the red path, right? So you all know refraction rules would say that it would take the red path, but why? So that's because light does an optimization problem, which means that nature itself solves an optimization problem every time anything happens, right? So another example might be, let's say, a molecule, right? So you all know water is the H2O molecule, but it has this kind of structure, which is, it has an angle of some 104 degrees between the 2 hydrogen atoms. Why that, right? That's because molecules naturally choose the geometric configuration of what's called least energy. That's another optimization problem, right? So nature solves another optimization problem throughout, right? Each molecule is really a solution to an optimization problem that you have not solved, right? So nature has solved it for free. It doesn't really, we don't know why nature does that, so that's really principles of the world or the universe itself, but at least we know that that's a very good way to summarize what nature does, right? So you define some functional and you realize that nature is already solving these problems. Right? Okay, so what are the elements of an optimization problem, right? So the first is the optimization variable, which is what variable do you want to take a decision on, right? So in the three examples that I mentioned, it's either the path to take or how much to study or the mode of exercise and distance, right? So that's the optimization variable. Then you have a domain, right? So this domain is typically just to say what is the data type of it, right? So imagine if you are writing a Python code, what data type would you use to store this optimization variable? So that's the domain. So it might be a Boolean, which means that it corresponds either left or right. It might be a real number, maybe it's numpy scalar. It could be a vector. It could be just a combination of a Boolean and a scalar. For example, in the case of mode of exercise and distance, it could be you have to decide whether to bike or walk, and you also have a real number which says how much you do that, right? So it's a combination of that. So imagine the domain as simply, for your convenience, as if you are solving this in a computer, what data type would you use for that? That's the domain. And finally, you have the objective, which is what do you want to maximize or minimize. So in the three examples, it was time taken or enjoyment or calories burned, right? So that's the objective that you want to maximize or minimize. And finally, you have constraints, which is what constraints are there. It's not, I mean, these three are necessary, but this is not really necessary. You have unconstrained optimization problems, right? Because, for example, let's say in the case of path to take, there are no constraints, right? So you can either take left or right, there are no constraints there. That's it. The constraints are, well, rather, there are constraints, but the constraints are captured by the domain itself, right? So it's not left or right or go straight through. You don't have the option of go straight through because that's not in the domain. In the case of how much to study, you have a total time less than 24 hours, and also the study time large enough to ensure, let's say, you get into IIT. And then for the exercise problem, it might be how to distance. It's bounded by exhaustion, right? So you have to ensure that you don't run so much that you fall, you faint. Right? So these are the four components, for the elements of the optimization problem. Right? So whenever someone says this is an optimization problem, you can, without, I mean, let's say this is another tip of the tricks of the trade. That is, let's say you go to a talk and someone says this is an optimization problem, and you have been sleeping for the last 20 minutes. Right? And suddenly you want to ask a question and get yourself up to speed. You can say, what is the objective of this optimization problem, right? Or what are the constraints of this optimization problem? And that's always a valid question, right? And they have to stop and explain what's happening there, right? So that's a good way to get a summary of what has happened so far, and still, so you're not asking a completely dumb question. You are always right to be. You don't need to worry that this might be a non-smart question. This is always a valid question. Right. So then you have types of optimization problems, right? So you can have based on the data type, which is a domain which is either discrete or continuous. Continuous generally means both scalars and vectors. So all of these things apply to both scalars and vectors. So you have generally three types of domains, which is either discrete, continuous, or mixed integer. So you do have solvers, right? So solvers available on the market, where if you write these four components in an appropriate mathematical or programming language, there are solvers out there which will give you a solution. Are they guaranteed to work? No, most of them are not guaranteed to work, but they will try to give you a solution, right? So that's true even for the real world, right? So you do have these problems and you do find a solution, but is that the best solution? Most likely not, right? So I'm sure that you overestimate how much time is required and you study too much, or underestimate how much time is required and you study too little. That's all going to happen, right? But you are aware what is your objective, right? So that's the case, and you do have these solvers. As long as you can express these four elements to the solver. The solver, let's say, is a software that you can buy on the market. There are open source as well as non-open source solutions that you can buy, and you can, as long as you give this in the right language, right? So you can't speak in English to a software, right? So you have to speak it in the right language. If you do that, it will get you a solution. But we are not going to do that, right? So we are not really going to use the software directly, because in a lot of situations, in a lot of specialized situations, you are better off trying to find the solution on your own rather than relying on a software, right? So in the scope of this particular workshop, we are going to restrict ourselves to continuous domain optimization problems. Discrete and mixed integer are an entirely different beast of their own. Right? They require very different techniques, so we are not going to go there. Continuous is a slightly gentler beast. You can try to tame it. We will have both scalars and generally its vectors are more general to have. So we will be working with continuous domain vectors as the domain. And then you have constraints, whether you can either have unconstrained optimization problems or constrained optimization problems. The focus will be on constraint. I'm kind of going to assume that you all know at least a couple of methods for unconstrained optimization. So before we go there, maybe you should just ask the question. Let's say you have an unconstrained optimization problem with continuous domain, right? And I give you a candidate answer, right? How will you check whether this answer is potentially correct or not? Let's say I want to say minimize f of x, right? So let's say f is a function from R3 to R, right? I know this, I give this function to you, and I also give you a candidate x star, right, in R3, right? And I ask you, okay, now can you tell me whether this x star, is this a solution or not? Is this a correct solution or not? Right? So how would you go about doing this? Any answers? Yes. I can't hear you. Can you speak up? Yes, that's more or less the right answer, but it is a function is a vector valued function. So if you differentiate it, what will you get? Right, so partial derivative means if you differentiate it, what will you get? What is the data type of the object that you will get if you differentiate it? It's a vector of dimension 3, right? So that's a gradient. You will see whether the gradient is 0 or not. If the gradient is 0, then are you sure it's a minima? No, right? But at least if it is not 0, what do you know? It is not a minima, right? So that's what's called a necessary condition, and that is really one of the essential tools itself, right? So that's these are called the first order necessary conditions. I'm going to just write down the short term, first order necessary conditions, and for most of the algorithms that we will be dealing with, what are called first order algorithms. Why are they called first order? Can anyone guess? But why are they called first order? Why not 24th order? That's my question. Why first and not 24th? Some arbitrary number. First derivative, yes. So the only information that you have about the function that you are using is the first order information. Right? So you have you have a function, but what is a function? Right? So a function means you have to represent the function somehow. Right? If I tell you store a function in a computer, how will you store a function? Can you store any arbitrary function in a computer? You have to represent it, right? So you have to find a way of representing the computer. So if I said, okay, up to 7th degree polynomial, you will store the coefficients of the polynomial. If I tell you that it's a weighted combination of a polynomial, 7th degree polynomial, and it also has sine x, e power x, and cosine x terms, you will have 3 other extra terms. Or you might have, as long as you know the parameterization of the function, then you can represent the parameters. But how? You must know the parameterization. So functions in general, it's not possible to represent arbitrary functions. In some cases you can. For example, there are these frameworks in Python where there are these functional building blocks that you have, right? So that is, you have something like addition, multiplication, subtraction, exponentiation, and then you have some basic trigonometric forms like sine, cosine, exponential, and you have other arbitrary, and you have these building blocks, and you can use addition, subtraction, multiplication, and composition, right? So you can say e power sine of cosine of x. You can do that because that's composition. So you can represent some functions as long as you use these building blocks. But why? These building blocks are just the building blocks that we are familiar with. What if someone somehow says there is a new building block out there, and I want to use that? You will not be able to do that. So generally, representing functions itself is a difficult task. So first order, in the sense that what is the first order information? So if you have a function f, first order information means that you have access to it's called an oracle. It's a first order oracle. It is you give some point, in this case of f from R3 to R, you might give let's say a single point, let's say 1, 3, minus 8. You might give this point and you have an oracle, right? So oracle, I mean, how many of you have heard the term oracle? Not the company Oracle, but rather, so the oracle, I mean, you might have heard of this in maybe Greek history terms. There is this oracle of Delphi and all that, right? So that is, they are supposed to speak to the god, and typically you have this oracle of Apollo and all that. So they speak to Apollo, and then the Apollo gives them a revelation, and then they convey it to the king, right? So that's the motivation for this term oracle. You have an oracle which can speak to this function, right? And then the king goes to the oracle and asks, okay, can I wage war? Will I win this war? And the oracle says, no, if you go, you will die. Something like that, the oracle says. So something similar is what happens here. You have an oracle and you have a first order oracle, right? So the first order oracle can only answer questions of a certain form, which is the first order oracle can take an x, right? It can take 1, 3, minus 8, and it can say what is the value of the function at that point and what is the gradient of the function at that point, right? So you don't really have access to the function itself, you only have access to the oracle, right? So the function is, the analogy is that this function is equivalent to the god Apollo, and let's say, and oracle is the priestess out there, and you can go and ask, okay, I have x, what is f of x, and what is grad f of x? So that's the only way you access the function. You don't really use the function itself. The function could have any arbitrary structure. It could have sine of, cosine of, e power minus x. It could have anything arbitrary. You don't really worry about that. You only access the function through the oracle, right? And this is typically the situation for most cases, because functions in all their glory and complexity are impossible for you to handle. But the moment you say, okay, I don't really care about the entire function, but I only care about accessing the function through an oracle, life becomes easier for you, right? So most algorithms that are designed are oracle based, right? So there are some functions, some algorithms that are designed which use information about the god or about the world apart from the oracle itself, but those we will not go into detail, right? So we'll ignore them. So that's why it's called first order necessary conditions. That is, whatever functions are out there in the problem, you only access those functions through first order information at a given point. So you don't use the entire function, you only use the value. So if you had a function if you had an oracle which could only give you the value, right? So which is, if you give an x, the oracle will give you f of x. Then that's called a zeroth order oracle, right? So that is, you don't even get first order information, you only get zeroth order information. So first order oracles are going to be assumed throughout, right? Anything more than that is unreasonable to assume. That's like assuming the structure of what you want to know. Right. So that's first order necessary conditions, and you have, unconstrained, I'm going to completely skip for the purpose of this lecture and focus on constraint. So constraint generally just means that in your 4 elements, you do have this element is present. You do have constraints. And then there are other qualifications, that is, if you have your function f is linear, if you have your constraints are linear, then it becomes what's called a linear problem. If you have your function and your constraints are quadratic, then it becomes a quadratic problem. In general, you also have convex problems. So I assume you are all familiar with a convex function and a convex set. How many of you here have never heard of a convex function or a convex set? 1, 2, 3, 4, 5, a few. Okay, fine. We'll ignore that for now. So convex functions are just a special class of functions similar to linear or quadratic. So I hope you all know what a linear function or a quadratic function is. Convex functions are just, a generalization. So we'll get to that when we get to that. And then generally you have the general nonlinear, where there is, you can say the function can be anything, the objective can be anything, the constraints can be anything. You generally have algorithms that work only when, let's say, the objective and the constraints are linear, or sometimes the objective. So each algorithm is typically designed for a special case, right? So you don't have a general purpose algorithm which will solve everything. So that's extremely rare. Even some softwares that you might purchase or download that looks like general purpose are not really, right? So they do a case-based analysis. If you give the question and then it will see, okay, whether is this linear, then it will use something else. That's all happening behind the curtain, but you don't have general purpose algorithms. Okay. So here are some examples again, I guess. So this is, you have a graph and you might say, okay, I have the goal is to go from this node to this node, right? So give me among all paths that go from this node to this node, give me the shortest path. So that's an example of an optimization problem. What's the domain here? The domain is sequence of edges. That's, you can say, well, this edge, and this edge, right? That's the objective is to minimize sum of edge weights. But there are some constraints, right? So not every sequence of edges is actually a path, right? For example, I can say this edge, and this edge. This is a sequence of edges, but it is really not a path from here to here, right? So that's, you can enforce that in a constraint, saying that, well, the first edge must be connected to the source, the last edge must be connected to the destination, and edge I must start at the endpoint of edge I minus 1. So these are constraints to ensure that the sequence of edges that you choose is a valid path, right? So that's why I made the point that the domain, you can say, well, why don't I just have the domain itself is the collection of paths from this point? You could say that, right? So why can't I just absorb the constraints of the domain? Can't I hide behind it? That's why I said that the domain, you don't really have that much freedom with the domain. Domain is just the data type that you have, right? So if you have, let's say, you're using Python, and if you have a fundamental data type itself that can represent paths, then great, you can go ahead and do it, but you are not going to be able to find it, right? So you might find tuples, lists, sets, you might find those, but you are not going to find paths as one of the fundamental data types. So you can't really say, I will use paths itself directly as the domain. So sequence of edges is fine. So you can have a tuple, that's a valid data type, but paths are not a valid data type. Because this is a very common question I always get asked, why not just put the constraints directly in the domain and be done with it? So can't I make every constraint problem an unconstrained problem by doing this? That's really just reframing the question and not really solving it in any way. Okay. Right. So then you have some other problems. I'm going to kind of jump through them. So you have a traveling salesman problem where the domain is permutation of 1 to n. Your objective is to minimize the sum of edge weights travel. There are no other constraints. So permutation is, you can argue that permutation is a valid domain by itself. You can find some programming languages where permutations are basic objects, right? So you can find data types like that, so that's possible. Then you have maximum weight matching. I'm having a lot of graph problems here. And then let's take the classic machine learning problem of linear regression. You have some data points, x1, y1, x2, y2, and so on. And the domain is set of all straight lines. So how is this a valid domain? That's because I can represent any straight line by an M and a C, right? So even though I say a domain is the set of all straight lines, it really is just a vector of size 2. And so M and C is all that I need to represent. And then what's your goal here? The goal is to maximize the fit, right? Maximize the fit. By maximize the fit, I mean you need to minimize the error there. So I'm not really going to go ahead and define what that is. You can clearly say, however, that this is a much better fit for the data than, let's say, something like this. So both of these are straight lines. This is a straight line. This is also a straight line. But clearly, this is a much better fit than this. You have to mathematicize this statement. How do you say what is the fit of anything? So there are multiple error metrics out there. We will get that, right? So there are no real constraints here. I think we can. What are the different stages that you encounter as, let's say, to use optimization? Right? First, actually the first and probably the most important stage is stage 1, which is how do you frame the optimization problem from real world requirements. Right? So that's actually the major part of your job, because once you have done this, you don't really need to worry about, at least to get some working solution, you can use some open source tools out there and just get it done. But the first part, no one's going to help you with. Right? So you have to look at the problem and come up with this framing yourself. And then let's say you're not using open source or some kind of software for doing this, then you have to convert it to a standard formulation and then find an algorithm for that formulation, implement the algorithm and check for correctness. Right? So these are all steps that you will do typically. I'm not really going to focus on the entire, I will do a couple of examples in greater detail towards the end, but most of the time we're going to just look at theory, right? So which is this, well, in fact, a significant part of the time we are going to be just working on this generalization. Right? So we had first order necessary conditions for an unconstrained problem, right? So told me that if I have an x and I can, what is the first order necessary condition? Well, I'll just compute the gradient of the function at some point x and I'll see if it is 0. So that's a necessary condition. If it is not 0, then I know it's for sure it's not a minima. But if it is 0, I still need to do some further checks. Right? What is the generalization of that for a constrained problem? So what's the generalization of, so does anyone know what is the generalization of this particular statement for a constrained optimization problem? Has anyone, I mean, I'm guessing that anyone who has done the MLF course should be able to answer this. So the first order necessary condition for an unconstrained problem is to just check if the gradient is 0 or not. But for a constrained problem, what is it? Is there a name for it? Pardon? Satisfy the constraints? Also, okay. Anything else? This is, there is a name for this, right? So this is to just get a sense of how many people know this so that I can cover this in greater depth or skip it. Right? Okay, so there are some terms coming there which are relevant, but what's the name for the condition? Karushkun-Tucker conditions, yes, KKT conditions. So how many of you have heard of KKT conditions? Okay, how many of you have not heard of it? So I do need to get a sense of how many of you. Okay, so a significant part of you have not heard of KKT conditions. So KKT conditions were covered in MLF, right? Yes, okay. So anyone who's raised their hands have not heard of it and still have done MLF course, need to do some introspection. Okay. So what is the, so for, so before we go to KKT, the first order necessary conditions for unconstrained, everyone knows that, right? So setting the gradient, checking whether the gradient is 0 or not as the first order necessary condition. Everyone has heard of this before today's lecture. Am I right? Anyone here who has not heard of that? Because at least the one-dimensional version of setting the derivative to 0 is, it is covered in school, right? I remember some applications of differential calculus, it's covered there. The multi-dimensional version might not be, but I'm guessing any bachelor's curriculum which has maths 2 or something like that would have covered this. So I'm going to assume that. So the KKT conditions is just that, the generalization of first order necessary conditions for a constrained optimization problem. Okay. A lot of people mistake KKT conditions as an algorithm by itself to find the solution. It's not, right? So it is just to check. The same way, seeing whether the gradient is 0 or not is just a condition. Of course, if you can solve for it, if you can solve grad f of x equal to 0, then it is an algorithm. But you might not be able to solve all problems, right? So if you have the ability to solve it, yeah, some gradients you can't solve. I can give some arbitrary function, you will have an arbitrary gradient as the expression on the left side. You can't really solve it, you can't really set it to 0. In some cases, you will be lucky enough to find that the gradient on the left side, okay, maybe before we go there, it might be good to, let's say you have a function f from R2 to R. Right? So let's keep it simple. Let's say f of x is equal to, say, x1 squared plus 3x2 squared plus, let's say, 2x1 x2, right? So some function like this. If you want, you can also add plus 3x1 minus 3x2. Right? So I want to minimize this function. This is arbitrarily, this is some second degree 2 polynomial here. So here, this particular function has a special property, which is if you try to compute the grad f of at x, what's that? Well, you take the partial derivative with respect to x1, that's 2x1 plus 2x2 plus 3, and here you have 6x2 plus 2x1 minus 3. Okay. Here, this is special in the sense that you can actually set the gradient to 0 and solve for it. Why is that? Because here, what you have here, this is the 0 vector, this is just 2 equations, 2 unknowns, you can solve for it. That's because you have the ability. So that's another fundamental ability that you have, which is linear equation solving. So the same way you can do multiplication, addition, subtraction, that's another fundamental ability that you have. But the moment I change things around and add things like, for example, instead of f of x being this, I also add a cubic term. So let's say I have 7x2 cubed, and then you add, for the heck of it, let's say I add e power cosine of x. Some arbitrary thing like this. Now you can still compute the gradient, right? You can even write it in some form here, but you will no longer be able to solve grad f of x equal to 0. Right? So checking grad f of x equal to 0, you can still do that, right? So if I say I give you this function and I ask you, is 5 comma minus 3 a minimizer, right? I can ask this question and I can still do this. I don't need to solve for it, right? So I just substitute, I compute the gradient, and then I just substitute this 5 comma minus 3 and check whether it's 0 or not. I can do that, right? So grad f of x equal to 0 is a first order necessary condition. In some special cases, you can also make it an algorithm because you can solve for it, right? But that's a very special case. Okay. So before we go there, why is this special? If you didn't have this extra thing, why is this special? Why can you solve for this but not this plus cosine x minus e power sine, something like that, right? Why can you solve for the gradient of this but not for the other? Yes. Yeah, that's it. That's all. It's quadratic. That's the answer I'm looking for. So if you have a quadratic function, then the gradient is, if you have a quadratic objective, then you can solve for the gradient. No other function you can actually. So that's the only kind of function for which you can solve for the gradient. Any other thing, it's generally not possible. All right. But that's still an important thing to be aware of, because quadratics are an important class of objective functions, in which case you can say grad f of x equal to 0 is not only a condition but also an algorithm, because you can solve for it. But in general, it's not. So how I said optimization problem, and I have been speaking in general application level things, but finally you have to go enter into the math, which is how do you represent a constraint optimization problem? This is typically how you do it, right? So you have an objective. For simplicity, we are going to always assume that our domain x is a d-dimensional vector. Right? So that's the most common domain that you will encounter in numerical optimization, where your optimization variable is a d-dimensional vector. Right? So that's the most common domain. I'm going to assume that throughout. Right? So you have all of these, and I'm also going to assume that whenever I use a function, these functions are all in the same domain, right? So you have a function f which takes in this d-dimensional vector and outputs a scalar. Right? So that's the objective here. And you have, let's say, m constraints, m inequality constraints and n equality constraints. Right? So that's the two kind of constraints here. You have inequality constraints and equality constraints. So you have these g1 of x less than or equal to 0, g2 of x less than or equal to 0, gm of x less than or equal to 0, and similarly h1, h2, hn, all of these are equal to 0. Right? So these are the inequalities, are the equality constraints. This is how you represent the objective and the constraints. Right? So you can have some English statement. You can say maximize the revenue subject to the risk not exceeding 5%. You can say this kind of English sentence, But finally, if you want to go to a computer, the computer will just say risk not defined, revenue not defined, and it will just throw an error at you. Right? So it's up to you to come up with the right mathematical formulation which expresses your objective in this form. Towards the end, maybe I'll just give one example of how you can do it, but that's really the bulk of your work, right? So if you are going to be, let's say, a machine learning engineer or some kind of applied engineer, and you're going to use optimization, the bulk of your work is going to be translating the English sentences that's coming out of your manager's mouth into a reasonable version, mathematical form that you can actually run. Right? But I'm assuming that that's been done now. So you have these functions, and you have the objective function, and you have the constraint inequalities and the constraint equalities. Okay, all right. So that's the concrete optimization problem. You also have what's called an abstract optimization problem, where you say minimize f of x such that x belongs to some set C, right? So where C is in Rd. So this is kind of the same problem, but just that I have abstracted away all these constraints into one set. Right? So the C is a subset of Rd. I just abstracted it away. Right? This is not really useful because the question becomes, how do you represent a set? So how do you represent a function? How do you represent? Sometimes it is, but most of the time you are representing a function, a set, by these inequality and equality constraints only. So this does not really help you algorithmically, but it can help you to get an abstract sense of what's actually happening there. So this is called a constraint. This is the feasible set. That is, what values can your optimization variable take? The set of valid values that your optimization variable can take is the C, right? So once you have that, then your constraints can be ignored because the constraints have already been captured in the set C. Right? So you just looking for the value within this, the variable within this set that maximizes, or for simplicity, you will always minimize the objective. You can always maximize also by just, instead of minimizing f of x, you can maximize minus f of x. That's the same thing. Finding the best. So once you have the set of feasible, this is called the feasible set. Let me just name that. The feasible set is represented typically through constraints like this, but you can, for the sake of abstractness, you can imagine that's a set already out there. And once you have, let's say, you have a yet unknown form of computer which can do real number computation, can do analog computation, then if you have that, and if you have a computer which can evaluate the function f on all points in the set, then you just pick the argmax. That's the argmin. That's what you would do. But of course, you don't really have such a computer. We have what are digital computers which can only answer in Boolean, right? So you can't really, you can't say, okay, evaluate the function on the entire domain or the entire feasible set and find the argmin, right? So you can find the minimum of 2 numbers, minimum of 10 numbers, you can do that. But if I ask you to ask the computer directly to find the minimum in the range of 0 to 10 real numbers, it really cannot, right? So that's not really a basic operation that digital computers are capable of. Of course, there might be an analog computer which can do that, and nature might be doing some version of it, but we don't have access to it, so we'll not bother about it. So then you have definitions of local and global minima. Right? So the global minima is what we are really after, which is we are looking for an x star in Rd. We'll call that as a global minimizer. First of all, x star must be feasible. Right? So I can't, if I ask you how many minimize the, so let's say it says maximize the chance of getting into IIT subject to me enjoying or something like that, and it says you study for 58 hours a day. Right? That's not really that might be the optimal solution, but that's really not feasible because that's not something which you are capable of doing. Right? So it says, so that's the first condition, that is x star must be feasible. And then you have that this f of x star. So that's the global minimizer, right? So it means that f of x star has to be less than or equal to f of x for all x. So that's the definition of global minima, right? Which is this particular x star is lesser than or equal to every other x in your feasible set C. That's the global minima, and that's really our goal. Our goal is to get a global minima. Right? So all algorithms, all principles are to this end, right? So if any principle or any algorithm does not help you to get this global minima, it is useless. Right. Then you have a slightly relaxed version of it, which is called a local minima, which is x star is a local minima if, again, x star has to be feasible. But in addition to that, you don't say it has to beat every other x. You only say it has to beat every other x in a neighborhood of x star, right? So this might be a good time for a figure. Let's say you have, let's say this is imagine it's a one-dimensional function. Right? So it's a one-dimensional function. You can have, let's say this is x1, let's call this. Here, x1 is the global minimizer, x2 is a local minimizer, right? So it is in the neighborhood of x2, let's say around this neighborhood, x2 is really the best, but it is not really the best if you expand, right? So x1 is, so this is, let's say, call this x1 comma f of x1. So you have x1 is a global minimizer, x2 is a local minimizer. All global minimizers are also local minimizers, because if it is beating everything, it has to beat its neighborhood, right? So that means a world champion has to be a national champion, right? So that's the logic here. All right. So that's a local minimum. So, and in fact, you know that for the unconstrained problem, we just said that grad f of x equal to 0 is a first order necessary condition. But for what exactly? Is it the first order necessary condition for a global minima or a local minima? So here's the other thing, right? So if you have, the moment you have first order condition, or let's say you have the oracle, if you ask the oracle information about x at some x, the only information that your oracle can give you is local information, right? That is, it cannot, if you ask the oracle, dear oracle, what is the value of the function and the gradient of the function at 1, 2, minus 8? And the oracle will tell you the value of the function at 1, 2, minus 8 is 18, and the gradient is 3, 8, minus 6, some number. That's what it will tell you. To get this information, the only required part of the function that is required for giving this information is only the local information around the query point. Let's say I think I said 1, 2, minus 8. That's in the neighborhood. Around that particular point, only the information you are getting. So there is no way you can get local information and make a global pronouncement, right? So that is, if I tell you that this particular point is the lowest, or rather, if I tell you the gradient at this point is 0, 0, that does not mean that this point is the lowest point in the Earth, right? So there are definitely the Dead Sea or Mariana Trench or other points which are deeper than this. But the 0, 0, I tell you the gradient at this point is 0, 0, then the only information that you have is that this is a local minimum, right? So you don't have any information, global information at all. But there are certain situations, certain properties of a function where you can convert local property to a global property. So the classic example is a convex function, right? So if you have a convex function, then local minima are also global minima. So we'll come to that later, but that's an example property. But without the convexity property, all these first order necessary conditions are all for local minima only. Okay. All right, so let's try to get the first order necessary condition here. Let's keep it simple for now. Let's say you have just one equality constraint. You have only one equality constraint, which is you want to minimize f of x such that h1 of x is equal to 0. It's just only one equality constraint. So here is the first order. I'll just tell you the first order necessary condition already, which is, first of all, what is the first order? I give you an x star, and when is this a candidate local minima? Well, first of all, h1 of x star must be 0. Why is that? Because it has to be feasible, right? So if h1 of x star is not 0, then it is not feasible. So obviously you need this. In addition to that, you have, if you didn't have the constraint, you would have said, well, is grad f of x star 0 or not? That's what you would have checked. But because you have a constraint, you don't do that, but you check whether grad f of x star is, if it is parallel to grad h1 of x star. Right? So grad f of x star is a vector. It's a d-dimensional vector. And similarly, grad h1 of x star is also a d-dimensional vector. So we will say two vectors are parallel if one is a scalar multiple of the other. Right? So you have phi 1, 2, 3 is parallel to 2, 4, 6 because they are a scalar multiple of each other. So these are the two conditions. Right? So if for x star to be a local minima, so this is very different from the unconstrained case. For unconstrained case, you are just checking whether it was 0, 0, 0. You can clearly see that if grad f of x star is 0, 0, 0, then it is always valid. Why is that? Because 0, 0, 0, the all 0 vector is a scalar multiple of any vector. Right? So you take any vector, I multiply that by 0, I can get 0, 0, 0. So that condition still holds, but the other way around does not hold. So we'll see a simple example. Let's say you want to minimize, it's a two-dimensional, I kept x plus y here for simplicity. So the optimization variable is this. Optimization variable is x comma y. Okay, so that's the optimization variable. X and y are real value. So let's say you want to minimize x plus y such that x squared plus y squared minus 1 equal to 0, which means that my x comma y lies on the boundary of a circle. So that's the black boundary here. What do you think is the answer? What x comma y minimizes on the circle? Which value minimizes, which is the solution which minimizes x plus y? So is it this point, this point, this point, this point, this point? So I give you 5 options. Which do you think minimizes x plus y? Let's make it option 1, option 2, option 3, option 4, option 5. Right. Let's say I give you 5 options. Which do you think minimizes x plus y? What about 1? What about 2? What can you say about 2? Does it? It doesn't even satisfy the equality constraint. It's not on the circle, so that really is not going to work. Similarly, 5. So 1, 3, and 4 are the only options. Now we have 1, 3, and 4. Out of these, which do you think minimizes x plus y? 4, right? So that's because in this case you just computed x plus y for all 3 things and you did that, but have the answer in mind. The answer is right, but just have the answer in mind. Now we can compute the, I've just evaluated at these 3 points now. So x1, x2, x3, these points. So x1, I compute grad f of x1. So the function is, objective is x plus y, right? What's the gradient? It's always 1, 1. It's because it's a linear function. So that's another property that you have to keep in mind. For linear functions, the gradient is a constant vector. So same way for quadratic functions, the gradient is a linear function. For linear functions, the gradient. So this is kind of just the same standard f dash of x that you already know, right? So if you differentiate x squared, you get x. If you differentiate x, you get a constant. So now that means that the gradient does not really depend on x. So it's always 1, 1. So I evaluate the gradient at this point, this point, this point. It's always the same. It is the 1, 1 vector. But that's not true for the grad h1, right? So I need, grad h1 does depend on x. So I can compute grad h1 at different points. Because it's a circle, you know exactly how it's going to look like. Grad h at this point is going to look like this. At this point it's going to look like this. At this point it's just the outward vector, outward normal to the circle. That's your grade. So it says that grad f of x star is parallel to grad h1. Of these 3 points, you have computed grad f and grad h for all 3 of these points. Is grad f and grad h parallel here? Yes, right. So obviously they are parallel here. Are they parallel here? Yes, they are parallel. They are pointing in opposite directions, but they are still parallel, right? So 1, 2, 3 is parallel to -1, -2, -3. They are pointing in opposite directions, but they are parallel. So, but x2 they are clearly not parallel. Right? So based on this example, you know that x2, x1, and x3 satisfy the first order necessary conditions. Right? But you know the answer is only x1, but x3 is also. If you just check the first order necessary conditions, you would say x3 also satisfies the first order necessary condition. Okay. Is there any questions on this? Okay. All right. Why though? Right. So why? I mean, first of all, why x3? Right. So why is x3 also a candidate? Can anyone guess why x3 also turns up here? Imagine the circle itself. If you move along the circle, how will this function look like? Let's say you are moving along this circle. How will this function look like? Sorry, this function. It will be the minimum here, and what will happen here? It will be the maximum there, right? So it's if you start from here, you will go on increasing. It will reach the maximum here and then start decreasing and come back here. That's what will happen. And so this actually is a property that you see even in unconstrained case. Right? So if you have the unconstrained problem and you have a local maxima, then also the gradient is 0. Right? So this obviously cannot deal with that. Right? So first order conditions, if you check for zeroness, you are only checking for a critical point. So maxima are also going to satisfy that. Okay? So that at least says why x3 also works, but that still does not say why this particular thing, right? So why should this happen? Why should grad f, why should the gradient of the objective be parallel to the gradient of the constraint? So immediately you should see one particular situation. What if I had linear functions and linear objectives, right? Let's say I said minimize x plus y such that x minus y is equal to 0. Okay. So I just give this. So what is, can I minimize this function? Can I solve this problem? So firstly, you can see that there is no way for you to satisfy this condition, right? So you can pick any x star which satisfies, but grad f of x star is always going to be 1, 1, and grad h of x star is always going to be 1 minus 1. So 1, 1 is never parallel to 1 minus 1. So you can never satisfy this condition. Why is that? So that means that this particular function does not have any minima at all. Why? Why does this not have a solution? Can you think of a graphical answer for this? So x minus y equal to 0 means that x is equal to y. That's where you are. I am telling you to minimize x plus y on the straight line of x equal to y. You can always, whatever point you give me, you can say minus 10, minus 10. I'll tell you why not minus 12, minus 12. You give me minus 100, minus 100. I give you why not minus 200, minus 200. So whatever point that you give me, I can always decrease it even further. So the answer is to this, the solution is actually unbounded. Right? So you can always go further. So that's the reason why you don't have any point which means this. Okay. But let's ignore that. Let's imagine situations where the function is bounded, right? So if the function is unbounded, then that indicates in a real world problem, you have made a mistake in framing the question, right? Let's say you want to maximize the revenue and you have come up with some surrogate for the revenue, and you find that in that function there is some value for which it is infinity. Right? Most likely you have either cracked capitalism itself, or you have made a mistake in converting the English statement of revenue into mathematics, right? So you should go and take a look at that. But for now, let's assume that's not happening. Now we'll try to understand this. Right? So even in this case, it still works. The condition is still working. There's nothing wrong with the condition, just that the problem was unsolvable. Right? So that is There is no minimum point. But if the problem is solvable, this condition is still meaningful. Why? So why should grad f of x star be parallel to grad h of x star? The way we'll argue this, I'm not going to prove a similar statement for everything, but this is a very easy thing to prove. So this will give you an idea of why this should happen. The way we are going to do this is as follows. Right? So I'm going to give a proof sketch. Right? So let x star be a local minima. Right? That is, let x be so this is what you're going to prove. Let x star be a local minima. Then we are going to prove this. This is the first order necessary condition, right? So if x star is a local minima, then it has to satisfy this, not the other way around. If this it satisfies this, it may or may not be a minima. But if x star is a local minima, then these two conditions have to be satisfied. Okay? Let's do that, right? So that's what you are going to do. Let x star be a local minima, and now we are going to show that, right? So how do we show these two things? If you want to show a logical statement, a classic proof technique is contradiction. So let's assume, okay, so this is obviously true. H1 of x star has to be 0, so that's don't need to prove that. This is the only thing you need to prove. Let's assume that grad f of x star is not parallel to grad h of x star. Let's take a point x star where, well, we assume that x star was a local minima. I mean, that's the starting point. And let's also assume that the constraints, sorry, the gradients are not parallel. Right? In that case, what will we do? Right? What we'll do is we'll actually find a direction for you to improve, right, while satisfying equality. Right? So you've given me an x star, which you say is a local minima, and you're also saying that the constraints, the gradients are not parallel. If you come up with this counter example, we say, look, I have this thing, your statement is wrong. What I will do is I will take a look at these two statements and I will say, well, that's not really there is a contradiction, because if you take your x star and move in this direction, I will still maintain equality, but I will have a lower objective. So you clearly, you have not given me a local minima. So that's the contradiction I'm going to do that. So this is what it is. There exists a direction u such that well, grad h1 of x star u is equal to 0 and grad f of x star u is less than 0. So what does this mean? So what does it mean to have this? Right? So use a direction. What does it mean to say grad h1 of x star transpose u is 0? What does that mean? H is the constraint. Right? So if I find a direction u such that grad h of x star transpose u is 0, then if I move a little bit along the direction of u from x star, what will happen to the constraint? It will stay 0. That's what this means. And grad f of x star transpose u is less than 0. What does that mean? If I move a little bit along the direction of u, yes. Right. So if I move a little bit along the direction of u, the function will reduce in value. So what I have found here is a direction where if I move from x star, I will keep satisfying the equality constraint, because equality constraint was previously satisfied and my h is not changing. Right? So I was previously x star satisfied the equality constraint. If I move along this direction, I will keep satisfying the equality constraint, but I will reduce the objective. So that's clearly, that means that x star is clearly not a local minima, right? So I have given you a direction of improvement. But how do you get this u? So that's a little bit technical, but this is one thing you could do, right? So you could say, well, I'm setting my u to be negative gradient of f plus alpha times gradient of h, where alpha is this scalar, right? Let's not worry about that. So once you have computed this, once you have set this u, you can compute your u transpose grad f and u transpose grad h, and you will see that this is true. And pictorially, this is what happens, right? So you have given me grad f and grad h, which are not parallel. I'm constructing a u like this, which is perpendicular to grad h. So which means that if I move along u, my constraint is not going to change. It was previously satisfied, it is still going to be satisfied. But I am moving in the opposite direction of grad f, so which means that the function will reduce. So what this says is, as long as my the constraint gradient and the objective gradient are not parallel, then I can find a direction which does not change the constraints but reduces the objective. So that's this u here, and by moving along this u, I will reduce my objective and satisfy the constraint. So that's clearly violating your statement that x star is a local minima, right? So if you say that x star is a local minima, I should not be able to find a direction of improvement, but I am finding a direction of improvement. So a contradiction, which means that if x star is a local minima, then your objective gradient and constraint gradient have to be parallel. Right. That's all there is to it. Any questions? So this is a special case of the KKT condition. All right. And okay, let's skip ahead to the next case. What do you have? One inequality constraint. So now it's the same. Let's say you have minimize f of x such that g of x is less than or equal to 0. Right? So for example, it can be minimize x plus y such that x squared plus y squared minus 1 is less than or equal to 0, which means that now the feasible set is the interior of the circle as well. Okay. So in this case, what is the minima? It's this again, right? So the answer is still the same. The point minus 1 by root 2 comma minus 1 by root 2. That's the minimizer. All right. And okay. What's the first order necessary condition here? What's the FONC for x star to be a local minima? First of all, it must be feasible. That is, your g of x star must be less than or equal to 0. And let's look at this constraint first. If g of x star is less than 0, strictly less than 0, then grad f of x star has to be equal to 0. Right? So let's try to break this this statement first. So what does it mean to have an x star whose g of x star is strictly less than 0? What does that mean? So let's say g of x star less than or equal to 0 defines this circle. If g of x star is strictly less than 0, what does that mean? That means that the point is strictly in the interior of this circle. Okay, so here or here or here. If a point is in the interior of the circle, then for all purposes, you can as well assume that the constraint is not there, right? So that is, the constraint is not immediately restricting you. Right? Your current position, it is as well not there. So it becomes an unconstrained problem, and for unconstrained problem, the FONC is simply you set the gradient to 0. So that's what you get here. So if your inequality constraint at x star is strictly less than 0, then you can as well have the fact that the constraint is not there and have your FONC simply reduces to grad f of x star is equal to 0. But however, if the other way around, if let's say g1 of x star is exactly equal to 0, that means in this case, for example, it can be on the boundary. So if it's on the boundary, then the constraint is impacting your current x star. So you can't really throw away the constraint does matter. So in that case, that's your case here. In that case, your grad f of x star has to be parallel to the thing, but not only that, it has to be pointing in opposite direction. Right? So that's the difference between the inequality and equality case. So it still has to be parallel, but in the case of equality, you didn't really care whether it was pointing in the same or opposite direction, but here it has to be pointing in the opposite direction. Or equivalently, grad f of x star is equal to minus lambda times grad g1 of x star for some lambda positive. Okay. So this is your first order necessary condition. Let's do the same thing here. So once again, you have 3 points x1, x2, x3. F has not changed, grad f has not changed, grad g has also not changed because it's the same function. Here once again, x2 you can rule out because it's not, okay, for simple, let's consider x4 also, right? So at x4, what is grad f, grad g? Well, x4, let's say the grad f and grad g are going to be, grad f is going to be the same, it's like this. Grad g, let's say, is like this, doesn't matter. So x4 is an interior point, right? So at x4, if you evaluated the constraint, it will be strictly less than 0. X squared plus y squared minus 1 is going to be strictly less than 0. So the only way for this to satisfy FONC is if grad f is 0. But grad f is not 0, so x4 is clearly not going to work. So now you have these 3 points, x1, x2, x3, which are all on the boundary. Right? We can once again compute the grad f and grad g. For x2, you have grad f and grad g are not parallel, so you can throw it away. For both x1 and x3, they are parallel. So are they both okay? In the case of equality, they were both satisfying FONC. But here, only x1 satisfies. Why is that? Because they are in opposite direction only at x1. For x3, they are, the grad f and grad g are parallel, but they are pointing the same direction, so it's not. So for this example, at least you know how to apply the FONC. Now comes the question again, why? Why is this the FONC? So we'll argue just with this example. I'm not going to go into the symbolic idea here, just examples. It's the same logic though, right? So you assume there is, let's x star be a local minima, and you're going to prove these statements. Okay? So if x star is a local minima, how do you prove these statements? Well, you assume the contradiction. Let's say you say, let's say this is not true. This is not true, then I am going to get a contradiction. How do you get a contradiction? It's the exact same way that, as previously. I will give you a direction which is both feasible and it's a feasible and descent. It's a feasible direction and a descent direction for an objective. DESCENT, right? So feasible descent direction. So this is really the key word that you are looking for here. At any point, if you want to say that this is not a local minima, you have to just find a feasible descent direction. Okay? What does that mean? That means that if you move along this direction, you won't violate the constraint. That's what the feasible means. And if you move along this direction, your objective will decrease in value. So that means that if you move along this direction, you are going to get a better answer than what you have currently. Right? So that's what you will do here. And you can see for these cases, let's say you are here, clearly I can find a feasible descent direction like this. If I am here, I can go along this. But if I am here, I cannot really find a feasible descent direction, right? So this direction, if I move along, my constraint is only going to get less violated, right? So I was at the boundary, I'm getting at the interior, so that's fine. Similarly here also, if I move along this direction, it's clearly a descent direction, it is also feasible. I'm moving inside the set. But if I am here, if I have to decrease the function, then it has to be some direction in this area. But if I moved there, I would move outside the set. So I don't have a feasible under descent direction. I might have feasible directions, I might have descent directions, but I don't have a feasible descent direction at this point. So that's the reason why this point is a local minima, but these two are not. And in fact, in this case, this is also a global minimum, right? And that's because of the special nature of this particular optimization problem. This is an example of a convex optimization problem. I'm not going to go ahead and define what that is, but convex optimization problems are such that local minima are the same as global minima. Right? So I'm going to skip that right now. All right. Okay, so that's fine. One equality, one inequality, okay. But what about two inequalities? Right? What about the general setting? Right? So that's where we started, right? So in the general setting, we had m inequality constraints and n equality constraints. How do you handle that setting? In fact, you already have the tools for doing that, and I'm not going to go into greater detail. I will share this notes. It's available already, I think, in some form or the other online. You can evaluate it yourself. You have, let's say, two inequality constraints, minimize f of x such that g1 of x less than or equal to 0, g2 of x less than or equal to 0. So take, for example, this set where you want to minimize x plus y such that x squared plus y squared minus 1 less than or equal to 0, which means that interior of the circle, and also minus y less than or equal to 0, which means that it's in the positive set. So this, you have two constraints. This is the one constraint, and this is another constraint. This is your feasible region. Here also you can have first order necessary conditions. So it will look like this, right? First of all, it has to be feasible, right? So if someone gives you an x star, it has to be feasible. That's your thing here. Then you have four possibilities, right? So which is, you have two constraints and four possibilities. Why is that? Because both of them can be active both of them can be inactive. One can be active, one can be inactive, inactive, active. There are 4 possibilities. What does it mean to say active? That means that these constraints are actually equal to 0. G1 of x star is equal to 0 and G2 of x star is equal to 0. And you could have both of them to be inactive, which means that G1 of x star is less than 0 and G2 of x star is less than 0. And you could have the mix and matches, which is this is less than 0, this is equal to 0, less than 0, and so on. So you have the 4 cases, and let's get the easiest case first. If both of them are inactive, then for all purposes this is an unconstrained problem. So the FONC just is grad of x star equal to 0. And let's do the next settings. If you have one of them active, other inactive, that's for all purposes the same as having just one inequality constraint, and for that we know the answer, and that is, let's say if G1 of x star is less than 0 and G2 of x star is equal to 0, this we will ignore. This can be ignored. You can just say, well, grad of x star has to be minus lambda 2 times grad G2 of x star for some lambda 2 positive. Similarly, the other way around, just swap 1 and 2. The interesting final case is, what if both the constraints are active? So if both constraints are active, then you have this condition which says that grad f of x star is minus lambda 1 times grad G1 of x star minus lambda 2 times grad G2 of x star for some lambda 1 lambda 2. So you can see that this looks like you have added these two and put them here. The right hand side you have, the left hand side remains the same. The RHS you seem to have added these two. That's what seems to be happening here, and that is correct, but why? So why addition and why not, let's say, multiplication? Why not division? Why not some other operation? Why this particular? And that really all boils down to the fact that we are doing first order methods, right? So first order methods are all linear approximations, and because of that, really what happens is the addition is the right thing to do. Of course, you have to prove this. I'm not going to prove this in today's session. You can look up the proof for it, but it's not really that much of a stretch to do this. And once you have this, okay, that's for two inequality constraints. But now what about the general case? What about the general case where you have m equality and m inequality constraints? Yeah. So the general case, you have m inequality and n equality constraints. What are the first order necessary conditions? That simply, first it has to be feasible. Okay, so let's call these feasibility conditions. There are 3 groups of constraints. This is the feasibility. Okay. And the second is that there exists a positive lambda and a vector mu. Okay. So inequality constraints, so you have the directions of the gradient, right? If it's an equality constraint, the only thing that matters is if it's parallel or not. But if it's an inequality, it has to be pointing in opposite directions. So that's important. So for each inequality constraint, you have your lambda, which is positive. But for equality constraints, you have just a mu. Okay? And the constraint is simply that grad f of x star is simply a weighted combination of negative grad g's and negative grad h's. Right? The weights are positive for the inequality constraints, but for equality it can be either, so it doesn't really matter. So this is how you write it. So this is, you have just put together, you've seen a couple of examples and we have put that together and done this. Okay, so that's the situation. But if this does not really capture the inactive constraints. So this assumes that all constraints are active or inactive. So to capture the fact that if, for example, take the extreme case where all the inequality constraints are not active at all. So that's equal to not existing at all. Right? So in that case, you must have these scalar multiples which are called the Lagrange multipliers. They must be 0. Right? So that is, if your constraint is, let's say, the ith inequality constraint is inactive, which means that GA of x star is strictly less than 0, then your lambda I, which is the ith Lagrange multiplier, has to be 0. Or in other words, you can write this, that is lambda I equal to 0 if GA of x star is less than 0. So that's perfectly fine, but typically it is written this way, which is lambda I multiplied by gi of x star is equal to 0, which means that one of these two has to be 0. That is, either gi of x star has to be 0 or lambda I has to be 0. Right? Both cannot be non-zero. That's what I mean. Both can be 0, that's valid, but both cannot be non-zero. What does that mean? That means that if gi of x star is non-zero, which means that this particular ith constraint is inactive, then the Lagrange multiplier for that particular constraint has to be 0. That's all there is to, this is called, well, let me write the names for this. This is called stationarity. And this is complementary slack. And this is what is called the Karushkun-Tucker conditions. Right? So I hope for people who know what KKT conditions are, this was a recap. I am taking way too much time, but it's fine. So we have another 30-40 minutes, which should be sufficient to just get you some basics of Lagrangian duality. Right. Any questions on this? Right. So I see some people have zoned out, so we can probably have a doubt session also, right? So that's also fine. So this is a perfectly valid place to stop and do more examples. So we can do one of two things. One is we can do more examples analyzing this KKT conditions further, or we can go and apply these KKT conditions into Lagrangian duality, right? So I'm okay with both, right? So this is really a session for you to learn, and in a typical lecture, let's say, that happens within IIT, we would actually do more examples and not try to cover more content. But I don't really know how much you all are familiar with KKT conditions and how much you want to learn about it. So I have both options open, right? So how many of you want to go further and learn more theory of Lagrangian duality and so on? 1, 2, 3, 4, 5, 6, 7, 8. Okay. How many of you want to make the KKT conditions more clear and have more examples and so on? That seems to be a clear majority. Some of you have not raised your hands for either, but the clear majority seems to be more examples. That's okay. That's fine. I have no issues. Right. Let's apply the KKT. Right. So one thing that you could do to make life a little bit easier, instead of writing it this way, is to define a secondary object which is called the Lagrangian. Right. The Lagrangian is defined as follows. Since you had the objective and the constraints, right? So which was just a function of x. The Lagrangian, on the other hand, is a function of x and a lambda and a mu. So what is that? L of x lambda mu is f of x plus sum over I lambda I gi of x plus sum over I mu I h I of x. So this is called the Lagrangian. The classic Lagrangian comes from balancing of gravitational forces of the earth and the moon and so on. But people have generalized that and realized that, well, Lagrange already did it for a special case of gravitational attractions, and this is just generalizing it. So we will give the general term also a Lagrangian, and that's right. So how does this help us? This helps us because instead of writing it in this form, you can write stationarity in a much easier way, which is you can just write this down as the gradient of, with respect to x, of L x star lambda star mu star has to be equal to 0. Okay? And then Ga of x star into lambda I star equal to 0. So this is just a compact way of writing feasibility. This is your stationarity, and this is your complementary slack. This will be the typical form that you will find KKT written in. If you go to a textbook, you will find this form written because it's compact and easy to write. But this really is the same as this. There's really no difference here, it's just the same. Okay. Fine. So one common issue that people have with the Lagrangian is why someone says, right now we have all in a standard form, right? So f is all, let's say, you want to minimize f subject to inequality constraints going less than or equal to g1 of x less than or equal to 0 and so on. But if suddenly someone comes up and a natural problem happens to be maximize f of x subject to g1 of x greater than or equal to 0, something like that, then suddenly if you are asked to write the Lagrangian, people just forget which should be positive, which should be, and then just guess what it should be positive or negative and then do something and hope that there is a 50% chance that they are right. That's a really bad way to do things. You should understand why these things are. That's the reason why I made some effort to give a geometric intuition on the inequality constraint. So it should point in. So here, that's the reason why for inequality constraints, here you had it should point in opposite directions. It was important that the gradient of the function f and the gradient of the constraint g are pointing in opposite directions. Right? So if it was pointing in the same direction, then I can find the feasible descent direction. So now instead of minimizing maximum, I change it to, let's say this was something else. Let's say, we had some other example. Or rather, let's draw a diagram. Let's ignore these. This is just the axis. Just the axis. So the constraints really don't stop here, they go all the way. So let's keep it simple and say minimize x1 plus x2, or rather let's make it maximize x1 plus x2 such that x1 by 3 plus x2 by 6 is less than or equal to 1, and then x1 by 6 plus x2 by 3 is right. So let's say now I've just changed the objective from min to max. So if suddenly immediately you are asked, okay, what is the Lagrangian? Of course, you could just change it to a minimization problem and say, well, instead of maximizing x1 plus x2, why not just change it to minimize minus x1 minus x2? So it's exactly the same. I mean, of course, the value is going to change, but the minimizer is not going to change. It's the same thing. But oftentimes you might not even remember whether it was supposed to be was the Lagrangian for the f, whether it's going to be minimization or maximization, whether it's less than or equal to or greater than or equal to 0, and you only know that often off the top of your head, just that for inequality constraints there is some extra thing, for equality there is something extra. How do you go about doing that? Every time if you have a doubt like that, always go to first principles and check whether the feasible descent direction works or not, right? So have a geometric idea and that will help you go a long way. I don't know why I went with this example, but it's not really required. So this is never guess when you are trying to construct the Lagrangian. Always, it just takes extra 2 minutes to construct a very simple example and then check whether your lambda is supposed to be positive or negative and so on. Okay. That's fine. I don't think we need to analyze that example. It might be better to analyze actually this example. Right. Let's say you have two inequality constraints, right? So you have minimize f of x, sorry, minimize x plus y such that x squared plus y squared minus 1 less than or equal to 0 and minus y less than or equal to 0. So you have these two constraints and you can do the same thing, right? So you can compute grad f, grad g1, grad g2, grad f, grad g1, grad g2, grad f, grad g1, grad g2 for the 3 points. Let's say x1, x2, sorry, x1, x2, x3. You can compute grad f and grad g1 and grad g2. Okay, so why would you, how would you, the goal is still the same, right? So if someone gives you a point and asks you, is there a first order necessary condition or not, you try to find a feasible descent direction. Let's say you are here. Right? How can you find a feasible descent direction? Right? Let's go the easy thing, right? Let's say you are here, you want to find a feasible descent direction. Right? So grad G1 and grad G2, what are they? If you say it is in terms of directions, if you move along grad G1, G1 increases. If you move along grad G2, G2 increases. So that's the definition of a gradient, right? It's the direction of maximum ascent. That's the definition of the gradient itself. So if you are here, if you move along grad G1 increases, this G2 increases. Grad f, if you move along this, f increases. So now what do you want? You want a feasible descent direction. So the moment you say descent, it has to be on the other side of this line. Right. And you have G1 and G2. Is G2 really an issue here? Right. So you are here, G2 just says that y is positive. Right. So you are here at 0, 1. At that point, y being positive is not really a constraint. So you can really just ignore G2. G2 is, so for all purposes you can ignore G2. So whatever direction you move in, you are not going to violate the feasibility of G2 because you are already well above the boundary of G2. So you can ignore G2 itself. So now you only need to worry about violating, need to find a descent direction that does not violate G1. That's the only thing you need to worry about. And this is G1. If you move along this direction, there is going to be an increase. So that means that anything which is here is going to be decreasing G1. And decreasing G1 is fine. Why is that? Because this is an inequality constraint, not an equality constraint. So you don't need to be perpendicular. As long as you decrease it, it's fine. So you can find a feasible descent direction, which is basically the intersection of this and this. So clearly there is a region here which is a feasible descent direction. So that's why x2 is not going to be a local minimum. Okay. Similarly, you can say the same thing for x3 also. But if you go to x1, this is your direction of ascent for the objective. So you need to choose something here. And because at this point, both the constraints are active, both G1 and G2 are active. So you need to move along a descent direction, feasible, when you say feasible direction, it has to decrease both G1 and G2, or at least keep it the same. It cannot increase either G1 or G2. So if you choose a direction, it has to have no component along grad G1 or grad G2. It has to keep both the constraints satisfied. So both these constraints, the value can decrease, but neither of them can increase, which means that you are completely disallowed from moving here or disallowed from moving here because of grad G1 and grad G2. So because you are disallowed from moving here and also disallowed from moving here, you can only move in this region. But if you move along that quadrant, grad f is, any direction in this quadrant has positive component with grad f, which means that f will increase. So you are not going to make the problem better. So that's the reason why. So that's all there is to multiple constraints. And anytime you have a doubt about directions and all that, please just have a diagram, right? So maybe this diagram itself will do, or even a simpler diagram. So the number of times I've had to correct papers where they just, whenever the constraint is given in a different format, right? So let's say here, whenever the constraint is given in a different format, they completely lose everything, right? So instead of this format, you say you give let's say someone use this. Of course, now you know exactly that you have to have minimization and less than or equal to constraints, but you might not remember this 2 months from now. In that case, it's okay. It's okay to forget things. That's not the problem. The problem is if you forget, and if you forget to apply logic. Right? So you can always have a figure here and then understand, well, what we are looking for is a feasible descent direction, and ensure that that works. All right. And another perhaps easier mnemonic to keep in mind might be this. Let's look at the Lagrangian, right? So this is the Lagrangian. The Lagrangian, you add up all the f's and the g's and the h's, right? The h's can be ignored, right? So for them, there is no problem whether you whether h of x equal to 0 or minus h of x equal to 0, they are the same thing. So it makes no difference. But for inequalities, it makes a difference. So you have to be careful. What are you really doing here? So you are trying to say the gradient of x with respect to x of the Lagrangian to 0. And you have positive coefficients for the inequalities. In other words, when you are, let's say your lambdas and mu's are fixed, you are looking for an x which minimizes the objective and also a weighted combination of the constraints, right? So if you had, let's say the problem was, you know the original form of the problem, but let's say in the problem now is minimize f of x such that g of x is greater than or equal to 0, and you have your L of x is L of x comma lambda is f of x plus lambda g of x. For a given x, for a given lambda, do you want to minimize this or maximize this? This is not a meaningful thing, right? So if it was less than or equal to 0, qualitatively you want to, you don't really care about g of x minimizing as low as keeping it as low as possible. You just want it to be less than or equal to 0. But qualitatively, you want to keep both f and g small. Right? So having f of x plus lambda times g of x is a meaningful thing, right? So and you say that I want to minimize f of x plus lambda g of x is a meaningful thing. But if I had g of x greater than or equal to 0, the moment you do this, f of x plus lambda g of x, this is not even meaningful. Do you want to keep this for positive lambda? Right? For positive lambda, what about this term? Do you want this smaller or larger? Right? But f you want to minimize, right? So there is a contradiction now. So this is wrong, right? So the moment you have this, then you must say that, well, that's the reason why you remember the standard form is always less than or equal to. So the moment someone gives you a greater than or equal to form and you write down the Lagrangian, for a given lambda, the entire Lagrangian must be coherent thing, right? So you want to keep it small or keep it large. You can't have two terms and one of them should be large, other should be small. The entire thing, is it supposed to be larger or smaller, it's not even clear. So that's why this is another trick for you to, it's not as strong a trick as the directions thing, because that's coming from first principles, but this is also using some logic to see that if you had greater than or equal to thing here and you applied and you did not know this and you apply Lagrangian directly, you should see that this Lagrangian for positive lambda is not really a coherent term, right? So you have one term which wants to be as small as possible and another term which wants to be larger than something. So this entire thing should be larger or smaller is not clear. So you should be for this to be a coherent term for positive lambda. Of course, if lambda is negative, it's still fine. It should be the case. Okay, right. So this is, I'm giving you mnemonics so that you don't make the obvious mistakes. Right. So these are. It always pains me to see mistakes like these, because that indicates that the student has not grasped the basic logic, right? So it's the same thing as in a probability question. If I see answer like minus 2.3 or 1.8, it pains me, right? It's okay to make some other mistakes, but if you get that answer, you should ring alarm bells, right? Saying that, oh, I followed all the steps and I'm getting that probability is 7.8, right? So what is wrong there, right? So you should always ask that question. All right, let's delete these. And now let's go for some examples. Okay, right. Here's an interesting example which is non-trivial. Right? So you have minimize x minus 1 the whole square plus y minus 3 the whole square subject to these constraints. So these constraints correspond to this diamond constraint. Okay. So what is this kind of problem? So this has a special name here. Can you give a geometric meaning for this problem? Let's just look at this figure and this constraint and tell me what would be a geometric meaning for this problem. So this is the feasible set satisfying, this yellow region is the feasible set satisfying these constraints, and 1, 3 is this point here. The solution that I am looking for is what exactly? This x comma y has to satisfy these constraints and it has to minimize x minus 1 the whole square plus y minus 3 the whole square. So what is that? Yeah. So distance, so that's exactly it, right? So this objective is simply the square of the distance between x comma y and 1 comma 3. So the square of the distance is minimizing the square of the distance is the same as minimizing the distance. We'll ignore that. So you want, what you're looking for is the point x comma y which lies inside this diamond and has minimum distance to 1 comma 3. So this is what's called a projection problem, right? So it is, you're looking for a point in this feasible set which is closest to some query point. In this case, it's 1 comma 3. So the answer in this case, you already know the answer, which is this. This is the answer. But you can consider the query, different query points. Right? Let's say this is the 0 comma 1 is the answer. This is x1. But there are also other points, right? So you could have 1 comma 0, which is, let's call it x2. You could have minus 1 comma 0, which is x3. You could have 0 comma 0, which is x4, and so on. Right? So you could have all of these things, and you can evaluate whether they satisfy KKT or not. Right? Let's go with x2 for now. Right? x1 we know the answer, so that's why we just do x1 and x2. For x2, how does grad f look like? So grad f is the direction of from which, so it's going to look like this. Okay. So if you move along this direction, your function is going to increase the most. Right? So this is the direction of steepest ascent for the function x minus 1 the whole square plus y minus 3 the whole square. So for this function, how will the contours of this function look like? Well, the contours of this function is going to look like this. And so on. So because the contours of function is going to look like this, the gradient is simply going to be perpendicular to that, and it's going to be like this. Okay. So that's your grad f, and you can see grad here. You can immediately see what are the active constraints. For x2, only 2 of them are active. The 2 of them are not active. So what are the 2 active constraints? Well, it's x plus y minus 1 less than or equal to 0. That's one active constraint. What's the other active constraint? Corresponds to this line, which is what exactly? Right. So one of these 3. I mean, I'm kind of blanking out right now. So you can find the other active constraint. So the 2 active constraints you have, you can compute the gradient, and you will find that there is a feasible descent direction. So which means x2 is not a local minimum. Right? And similarly, you can do the same thing for x1, and you will find that there is no feasible descent direction. And that means that x1 is in fact a local minima, and it also happens to be a global minima because this also happens to be what's called convex. So this is how you typically solve most optimization problems. Solve is a strong statement for this, but you are just checking whether a given point satisfies FOMC or not. And that is really half the job, right? So if you don't even have the ability to check whether an answer is correct or not, you can forget about solving it. I think we only have 15 minutes, which is just enough time for me to explain one simple problem. So, all right, let's have a simple example here. Here is an example problem. I think we are at the last stretch here. You have, let's say you have some money to invest. Right? So you have, there are, let's say, 4 stocks out there. Let's say there's TCS, Infosys, Wipro, and Reliance. Let's say there are these 4 stocks there. And let's say you are omniscient. That is, you know exactly the random variable that these are coming from. And you know, for example, let's say TCS, let's say what you are looking for is the profit after 1 year. If you invest, let's say 100 rupees now, what's the profit after 1 year? And you ask this oracle, and then the oracle says it's random, but it's exactly this distribution. It says that if you invest 100 rupees after 1 year, the profit from TCS is a normal distribution with mean 20 and variance 10. And it says Infosys and Wipro are not only the same distribution, but it's exactly the same random variable. Right? So maybe it says that all 3 are so strongly correlated, they are exactly the same thing. And then you have another thing, let's say it's Reliance, which is, let's say, another random variable, which is independent of the rest of these 3, but it is a normal with mean 10 and variance 5. Okay? So it's obviously unreasonable to expect you to know this information, but let's say you know this. Now here's the question. I ask you, you have 100 rupees, which percentage will you invest where? Right? So let's get the answers out of the way first. Right? Let's say you know this. Right? You have 100 rupees, where will you invest? Okay, you've jumped a couple of steps, right? So let's get to the easy answers first. What would you do? Pardon? I can't hear you. Okay, but isn't X4 lesser profit than, so if you invest in X4, isn't that the profit is only 10? Pardon? It's diversification, but why is that? I mean, don't do something because for the sake of names, right? So I want a concrete answer. Why would you want to do that? Right, so I understand your statement, but I want you to give an answer in terms of the numbers here, or in terms of the properties here, right? So that is X1 and X4 are independent. Right? The answer is you are right there, but let's ignore that for now. Let's say you are totally risk neutral. You don't care about risk. You only care about maximizing your average returns. In that case, what would you do? Put all your money in either TCS or Infosys or Wipro. It doesn't really matter. All three are the same, right? So you can split it 1/3, 1/3, 1/3, or full in TCS, full in doesn't really matter because all three are the same. You can do that. But let's say you are not totally risk averse, right? So you want to do this diversification or okay, that's a good strategy to have. That is, let's say if the IT sector falls as a whole, you still want to have some money left at the end of it, right? So that's the goal there. But how do you express that mathematically? So that's the goal of this particular example at least, right? So that's a English goal, but how do you convert that into a math goal? Okay, so let's evaluate the three steps. Let's say the strategy is, what is strategy 1? Strategy 1, you invest all in on TCS. So you put everything in TCS. What is your profit at the end of it is also going to be a random variable. What is that? Well, that's going to be exactly this. That's going to be your profit after you do strategy 1 is also a normal variable with mean 20 and variance 10 because that's exactly what's happening. Let's say the other strategy 2 is 50% in TCS, 50% Reliance. That's what you do. What's the profit there? Well, that's also a random variable, but what's the, let's say you do 50% here, 50% here, what is the random variable, what's the profit random variable? Is that's also a normal, but what is the mean, what is the variance? Mean is simply 20 plus 10/2, that's 15. Yeah, so half into 20 plus half into 10, which is 15. That's your mean of the profit. But what about the variance? You have to square it, right? Yes. So if you do that, that's 1/4 times 10 plus 1/4 times 5, which is 3.75. So now you immediately see the issue with these two strategies. It's the first strategy, you get a higher mean profit, 20, but a variance of 10. But in the second strategy, you get a lower mean profit, but a higher variance. Sorry, lower variance also. So there is no immediately, I mean, if you had a strategy which had a higher profit and lesser risk, obviously that's a dominating strategy. It's always better. But based on these two, you can't say one is better or two is better. You can't really say that. That depends on what your risk profile is, right? Let's say you're a highly risky investor who wants to get maximum returns every time. That is, you have, let's say, a long time to live, or you know that you're going to live for a long time and you are planning for a long future, in which case that's what you should do. But let's say you are an 80-year-old person and you can't really afford the risk of even a small chance of you might lose some money. Right? So you don't care so much about the average reward, but rather also the worst case scenarios. You are also worried about that. So based on that, these two strategies can be different, right? So of course, strategy 3, where you invest everything in Reliance, is definitely worse, right? Because let's say strategy 3, which invests everything in Reliance, is definitely worse than this, right? So 10,5 is 15 is greater than 10 and 3.75 is less than 5. So this strategy Y3, which invests everything in Reliance, is clearly not right, because not only is it giving lesser returns, but it also is more risk than Y2. But do you choose strategy 2 or strategy 1? So that depends on your risk profile or what your risk appetite is. This is typically captured by some, so if you go to some kind of online tool, they'll say, okay, what is your, they'll have some slider saying that, okay, what is your risk appetite, right? So is it high risk, low risk, and so on, right? And that is typically, let's call that a scalar variable, and that is controlled by, instead of, what you might want to say is, how do you calculate the risk though? What is risk? Well, one simple way is risk is simply this number. I want to minimize this, so I want this number as small as possible, but this number as large as possible. That's your goal. So a very reasonable thing might be to say, minimize this subject to this number, this risk number, or rather the variance of your returns being less than or equal to something. Or another thing that you can say is, I want to minimize the weighted, minima is the weighted combination of, let's say, the negative reward and plus risk. That's another valid option. Right? So let's write down both those cases. So now let's come to the math part of it, right? So we are still assuming that you have complete knowledge of the random variables of x1, x2, x3, x4. That is, you know the joint distribution of x1, x2. Not only do you know the individual distributions, but you know the joint distribution of x1, x2, x3, x4. In that case, how would you, that is, let's say your x, which is your original thing, is distributed as normal with, let's say, means mu and covariance sigma. And what is your optimization variable? Your optimization variable is, let's call it an alpha, right? Alpha is in Rn, it's an n-dimensional vector, but you can't really put minus 100 money in anything. And you can't put $1 billion when your total money is only $1,000. Right? So you can't do that. So let's keep it simple and say that, well, alpha I has to be greater than or equal to 0, and sum over I alpha I has to be equal to, let's say, 1. This number can be anything, can not be 1, but for simplicity, right? This is your domain, and this is your constraints. Okay, so what's the objective though? Right? If you have alpha is the fraction that you're investing in, alpha 1 is the fraction investing in TCS, alpha 2 is the fraction investing in Infosys, and so on. What is your returns though? Return is simply sum over I equal to 1 to n, alpha I are expected returns. First, let's write down the return itself. Return is a random variable. Why is that? Why is the return random variable? Because the returns on individual stocks themselves are random variables. So a weighted combination has to be a random variable. So the return is a random variable given by, I think we are slightly over time, but we should be. It's a random variable. Sum over I equal to 1 to n. If I xi. Let's call this y per. Okay, so now what's your goal? Well, your goal is to, let's say, minimize, let's get the expected return first. The expected return is sum over I equal to 1 to n alpha I mu I, right? So because of linearity of expectation, you have expected return is sum over I equal to 1 to n alpha I mu I, okay? What is the variance of return? Here is where things can get a little bit tricky because we have not assumed that x's are independent. Right? So x's can be, so in this case it was easy because we assumed that x1 and x4 were independent, but in general you have sum over I alpha I xi, and xi's are not independent, but you know exactly how they are dependent, so you can still handle this. Right? So what's the variance of the return? Well, that's simply expected. Let's write down expected value of y squared first. So ey squared is what? Expected value of so you can expand the terms inside and do all that, and if you do all that, what you will get is the expected value of y squared is simply what is this? Expected value of x transpose. So x is a vector, number of stocks, n-dimensional vector. X transpose is the matrix. It's not exactly the covariance matrix because the means are not 0, but it's very related to that. So alpha transpose x. And similarly, you have, say, if you had ey the whole squared, you will also get something else. Right? So ey squared is
So what is Ey squared minus Ey the whole squared? What is that? That's your variance of y, and that's simply going to be alpha transpose this minus this, and what's that? That's exactly the covariance of x, and that's simply going to be alpha transpose sigma. Right? So now your variance of y is simply alpha transpose sigma alpha. So now we have a mathematical form, right? So you want to maximize this subject to this being small, right? Or in other words, you want to maximize over alpha, alpha transpose mu such that alpha transpose sigma alpha, let's say, is less than or equal to some number, some variance that you have in mind, which might be, let's say, some number, let's call it 5, doesn't matter. And this number is what the slider is going to be. Why is this not working? If you are going to a tool and there is a slider, this number is what is going to be represented by that slider. Once you have that, you have sum over alpha I equal to 1 and alpha I is equal to 0. These constraints you will have, these will not change. You will have a slider, but of course if you say, well, I want to keep the risk to be 0, right? So typically you can always keep the risk to be 0 by investing in nothing. Right? So that's, you can keep it in a box under your trunk, and that's 0, right? Of course, you can go as high as possible. So that will always be an option where you don't invest anything at all. So that means that this number can be as low as 0. If you say, well, I want 0 risk, typically you will have to keep everything in your box. If you can say, well, I want the highest risk, right? So if someone says, okay, this risk is as high as possible, let's say it's in the example 1000. In this case, your risk appetite is quite high, in which case you will invest everything. In the example that we saw, you will invest everything in, let's say, TCS or in single stock. But if your risk is 0, you will invest nothing, right? So you will in fact keep it in cash. But somewhere in between, you will have, you will say, okay, I am going to split my investment so that some portion of it goes to TCS and some portion of it is in Reliance. But what portion? That depends on your risk appetite. Yeah. So now this is how you would convert a real world problem, saying that maximize return subject to, maximize low risk return is an English statement. How do you convert that into a mathematical problem so that you can build a software that with a slider and an interface? So the user does not need to know this. The user just has something saying that, has a slider saying that risk appetite. That's the only slider that the user sees. Right? You don't even need to name these axes. So you don't need to say 0 or 10 or 1000. You can just say 0 risk, low risk, medium risk, high risk. You can have 4 options and you can give them that. And then they'll just choose them. The user does not need to know the mathematical details of that's going inside it. But you, however, you have to solve the problem. So you can't say you find the low risk, high return strategy. That's English. A computer cannot do it. You have to convert that into math. And this is one way you could do it. And this is an example of a linear objective with quadratic constraints. And these kind of problems can be easily solved. Right? Using the tools that we have seen today itself, I have not really gone to the algorithm yet, but you can use these tools to build algorithms for solving these kind of problems. Okay. All right, so with that, I think this is a good point to stop. I'm sorry that I could not cover algorithms for constraint optimization, but I would say that algorithms you can always pick up. Right? So that is, but the fundamentals are something which you should get up to scratch if you are going to be using and building these tools on your own. So if you're using a software, then this is perhaps the most important thing. How do you convert an English statement into a math problem? But the fundamental things like the Karush-Tucker conditions, the first order necessary conditions, the Lagrangians and so on, those are also very important if you are going to build an algorithm from scratch. I think this is a good place to stop. Any questions? If there are no other questions, let's wrap, and thank you very much. Vote of thanks. I've already thanked everyone. Oh yeah, I should. Right. So mainly, I'll have to give my profuse thanks to Bharati, so who's been the pillar behind the entire program, and also I don't know how she gets so much time to do so many things. So she was the one who pushed all the teachers to give these sessions so that you guys have a taste, because most of you are, I'm guessing most of you are studying in colleges. How many of you are studying? How many of you are working? How many of you are studying? Can you please raise your hand? How many of you are working elsewhere? Okay. So I see significant majority of you are studying somewhere, and some of you are working. So to get a taste of how in-person classes look like, right? So you've all been through online classes a lot, you've all been through TA sessions, but it might sometimes feel like you are missing out on the in-person lectures, which is good, but not, the value add that it gets is kind of intangible. And to get you a taste of what's happening, so Bharati really pushed hard to get you guys as many options as possible, so that you have nice workshops throughout the day. And a lot of my thanks goes to Bharati and the team here. They have been like pushing me to, do you have tablet or not, do you have projector or not, all these logistics that we pushed to the last minute. The assistants Karthik and Arun have been doing, and thank the camera crew as well. I don't know who else I am supposed to thank. Right, and thank you all for turning up. So I hope you all have a fun time and finish your diploma or degree or whatever your goals are. And if you have any doubts on the content or on the general syllabus, feel free to contact me. I'm not very prompt in replying to a lot of emails, so feel free to send a repeat email if you really want my response. Sometimes it just gets pretty overwhelming, get tens of, 20s of, hundreds of emails sometimes. So if you want to really, this is a good time to catch me as well. So you can catch me now and ask any specific doubts that you might have. But even otherwise, you can just send an email to any of the instructors. They are not obliged to reply, because it's very difficult to keep track of everything. But if you have anything interesting or anything important that you want to convey, you can always contact us. All right, so thank you everyone. Yeah.